Start, okay. So if you look back at this proof that I gave, this proof really was based on Poisson summation formula. So yeah, as I said, it was based on two things, right? One was Poisson summation formula. The other one was this theory of modular forms, in this case, elliptic modular forms. But let's just focus on the first one. And yeah, so this was like, so let me write both components of the proof, elliptic modular forms. Okay, so now, so this PSF, as I said, it's an example of a trace formula. So then, of course, this begs the question, what is a trace formula in general? I mean, it's a good idea to stop a little bit and think about this question. So, so the question we first want to address is, what is a trace formula? So we want to address this question in kind of bigger context, more general context, and see what we can do, what we can learn. Okay, so here's an example. This is, I call it, it's kind of primordial trace formula. Primordial, I don't know if that term is really suitable, but I just use it. Primordial trace formula. It's kind of mother of all trace formulas. So what is this? So if you take a matrix A and then of C, for example, you have this equality that sum of AII, sum of the elements on the main diagonal is equal to sum of eigenvalues, right? Okay, so this is really the first trace formula, if you want, and it's kind of model of many trace formulas. So as you move in mathematics, move on, it becomes more and more complicated as you move on. But essentially, a trace formula is an identity that computes trace in two ways, right? So here is, we call this side the geometric side. And this side, obviously, is called the spectral side. The two sides are very different in nature. Notice that this geometric side, if you have the matrix, is easily accessible. You just take the matrix and sum elements on the main diagonal. But the spectral side, each term in the spectral side is not accessible. These are eigenvalues, and eigenvalues are very hard to compute, as you know. A 100 by 100 matrix, each eigenvalue, it could be very hard to compute. Nevertheless, the sum of eigenvalues is very easy to compute. It's given by just summing elements on the main diagonal. So this is this formula, though I mean it's elementary linear algebra, you might say, but it's a very deep identity. I want you to think about it as you're you're going about your business today later on, but just think about this identity. This is something quite deep, if you think about it. Okay, so this was example one. So some geometric thing, I call it geometric, and I'll argue later on that it is really more geometric. And this side is completely spectral, and the two sides. So this is the first example of trace formula. So let's look at example two. So this example is similar, except that now let's fix a function. We generalize this to infinite dimensions now. So take f belonging to L2 of x cross x. So this is a measure space, and you take L2 function on the measure space, product with itself, and then you define this operator AF, which is going from L2 of x and mu to itself. So to start with, x and mu is a measure space. Just think of interval 0, 1 with Lebesgue measure. That's good enough. That's really as deep, as difficult as it can get in this sort of more general case, right? So just think about that case, AF. So this is an integral operator. So I'm going to call it K, sorry. This is a K maybe. With kernel K. So it's defined like this. A K of F at x is equal to integral K of x and y, f of y, dy over x, right? So AK, as I said, goes from L2 to L2, and it's of this form. So if you have a function, you just integrate it against this kernel for each x, and then you get a new function of x by integrating with respect to y. So if you look at this expression, this is exact analog, infinite dimensional analog of this, because this Aij entries of the matrix here is replaced by kxy. So we have replaced discrete variables with continuous variables. The thing is replaced by that, and this is like a matrix that is multiplied by this column matrix that are just all entries of this column vector, if you imagine f at different points as this values. Of course, it's formal analogy, it's not a very exact analogy, but it's otherwise it's just a perfect analogy between the two things, right? So we have that.
Just clarification. You write A sub k is an endomorphism on L2 of x and comma what? Is it mu?
This is a measure, right? Sorry, this is a measure on the space x. Yeah, it's you can think of probability measure or just a measure. It doesn't matter. Just a measure, right?
Okay, thanks.
Sure. No, that was a good question. Okay, now so we have that. So now, so we have to use some general facts, which is not easy, which is not difficult actually to prove. And the fact is that this AK is actually trace class. Is trace class operator. So, so trace class, the formal definition, again, it doesn't matter. I want to rely on your intuition. Trace class is something that, for example, if you can write it in diagonal form as an infinite matrix, the elements on the main diagonal, for example, is just summable if you write it in some good basis, something like that. The exact definition doesn't matter because I don't want to go into functional analysis side, and it's not very difficult anyhow, but let's assume that this fact is, we understand, we have a fairly intuitive understanding of this fact. Then the question is, what is trace of this guy, right? then its trace actually can be computed by a formula which is like this side. So then add.
Is it in the trace class though? Shouldn't that be Hilbert-Schmidt?
This operator is, yeah, you're absolutely right. This operator is Hilbert-Schmidt. Yes, this is a very good comment. This is, in fact, all we can say is Hilbert-Schmidt is not necessarily trace class. But if it is, for example, continuous, then it is trace class. Imagine there is some topology on X, and so I'm going to assume that actually this is, in fact, continuous. So in L2 intersection continuous functions, for example. Yeah. And there is some decay at infinity, and so I want to assume that this is trace class. In good cases, it is trace class, really. So yeah. So this was a good point. So I went a bit too fast here, right? But then what we know is that trace of this guy is given by integral k of xx d mu of x. Which I just drop sometimes. I just write dx actually, just to make life easier for myself over x. And of course, this is the geometric side, right?
Is this a definition of the trace?
No, of trace. So the definition of trace, it's not this. The definition of trace is the formula that tells you if your operator is trace class. If you write it in some basis, then sums of elements on the main diagonal is going to be that trace, and then you prove a little theorem, little lemma, that this presentation, the sum is independent of choice of basis, orthonormal basis, for example. That's the original definition. It turns out that you can show that this is equal to this given by this in good cases. Yeah. Is that okay?
Yes, thank you.
Okay, so we have this, and you notice that this is exactly analog of sum AII, right? So it's like we are taking summing along the kernel. I mean, just sorry, along this IXX means II, and sum is replaced by integration, and of course K is the notation for A. I mean, so this is perfect continuous analog of this formula. And then the right-hand side also, it's so there is this Litsky's theorem. This implies that, in fact, integral k xx dx is equal to sum of mu, lambda I. So what is lambda I? This lambda I is in the spectrum of this compact operator AK, and because it's trace class, it's a compact operator. Again, this detail doesn't matter for us right now. The spectrum is discrete. Each non-zero element in the spectrum has finite multiplicity, and you sum them in any order you want, and you're going to get the same element, which is this left-hand side. So this is the spectral side. And this is, of course, the geometric side, right? So this relation, now this Litsky's theorem is a difficult theorem of functional analysis. So I don't downplay this theorem, because to prove that in linear algebra, to prove that sum AII is equal to sum lambda I, you use determinants, right? And you use determinants, you wrote down the characteristic function. I guess it's called characteristic polynomial. It's a polynomial of degree n, and you compare terms on both sides and you derive that function. But there is no, we don't have access to determinants in infinite dimensions. So Litsky have to give some ingenious arguments. And then there are people who also invented some proofs based on infinite dimensional determinants. So you can read all about these different proofs in Barry Simon's book. It's called Trace Ideals and Compact Operator or something. But yeah, he has like a short book, maybe 100, 120 pages, wonderful book by Barry Simon. So I recommend that book if you want to know about Hilbert-Schmidt, trace class, ideals of compact operators, these aspects of functional analysis. These are all there. So, okay, but now just moving a little bit intuitively because I'm not. This is not about the course. So this is okay. So this is a trace formula. So it's a kind of, again, for us, it's sort of primordial trace formula. It's not really the trace formula that I have in mind. Now, the claim is that this Poisson summation formula is an instance of this relation. Okay, so it's really Poisson summation formula is telling us that this, yeah, I mean, there are two sides. There's first of all, there's an operator somewhere, and what it says is that it computes the trace of that operator in two different ways. One as sums of eigenvalues, the other one as sums of this, I mean, integrating the kernel over the main diagonal, over the diagonal. So that's the content of the claim. I mean, this is not obvious at all, right? So let us recall Poisson summation and see what this is telling us. So recall this PSF. So in the version that I gave, we had this lattice in Rn. And I fixed a function, say, Schwartz class functions on Rn, but I said that even that sort of rapid decay is not necessary. Some decay is needed, but not so much rapidly, but that's okay. And then what was the formula? So the formula said that sum f of gamma in gamma is equal to 1 over volume of gamma, sum of tilde, hat, rather, k belonging to gamma star. So this was, I mean, the original Poisson summation formula that I derived, right? And then we applied this formula in the particular case of Gaussian. So anyhow, so let us look at this formula. So that's the formula that I gave a proof. There was a little bit of nuance in the middle, but that was easy. I told you to fix it. I hope you did. So this f hat is the Fourier transform. Of f, right? And gamma star is the dual lattice, and this is what we have, right? By the way, I mean, this formula, you may see it's also written in a different form, which is kind of inspiring to think about it that way. It just says that sums of Dirac masses, so this is Dirac function shifted by lambda, is equal to sums of Fourier transforms of Dirac masses shifted by k belong to gamma star. So this formula is the same as this formula. So of course, here I have written it as equality of distributions, right? So this is a, if you want, is a tempered distribution on the left-hand side. And this thing also on the right-hand side is the Fourier transform of this distribution. So, and there is no there's no need to put 1 over volume of gamma because this is already absorbed in Fourier transform of this distribution here. And this is equality of these two things is pretty straightforward. If you know the definition of distributions, if you don't care, that's fine. I'm not using it. I just say that maybe you will see something like that. But it's kind of interesting to look at it like this because what it says is the following. So, so imagine you have this. So, okay, I'm going to draw one-dimensional, unfortunately. So imagine you have a lattice of length A, for example, right? And what is this distribution on the left-hand side? You have this kind of sharp-peaked functions. So it's just like someone is sending signals, but the signal exists only at the lattice points. It picks up huge value and then dies, and then picks up. Okay, so the thing is, this signal and its Fourier transform are the same, basically. So that's what. So of course, now you have to go to dual lattice. You have to divide by 1. So this is 1 over A, 2 over A, so on, and then you pick up this. It just says that Fourier transform of this. I mean, yeah, term by term. If you sum, you're going to get the equality of these two things. Of course, individually, the Fourier transform of delta you can define by acting delta on the Fourier transform of the functions. So there is this kind of equality of comb functions or something like that. Anyhow, so but that's just a side remark. I don't need it right now. I just mentioned it. But now the focus is to see why this is an example of this. All right, so that's the point. So where is the operator here now? What is the operator? So if we can kind of write it in this form, we have a good chance of generalizing it to more general contexts. And just to save myself some time, so let me just use my notes because the operator, okay, so the operator is actually, okay, so the operator is the following operator. So let me write it. It's a convolution operator. So what do we have to start with? Of course, we have the lattice, but also we have this function f, right? So this function f, let us define this operator LF. So this LF is going from smooth functions, for example. So if you want L2 of Rn mod gamma to L2 of Rn mod gamma. Now remember, okay, so this is a flat torus. This is a flat torus. This is a group, right? It's an abelian group. So I'm saying an operator like that. So what is this operator? It's just LF of G equal to F convol with G. So this is the convolution product. So what is it? So it just means that LF G of X is equal to integral of F of, say, X minus Y, G of Y dy over R, which is also equal to integral of f of y, g of x minus y, dy over r. Yeah. So let's think about this. For example, y. So now, how should I think? How should we think about g? Okay, so g, of course, is a function. You can imagine first is a function on the torus, but you can also imagine is a function upstairs, or you can lift it upstairs and look at it upstairs. So it's a gamma periodic function in the upstairs, right? So then, so this is over Rn, by the way. This is Rn. So as a gamma periodic function, and this is a rapid decay function at infinity, so this integral is pretty good. It's fast convergent. But the question is why the result is gamma periodic. Well, it is gamma periodic because you see what we are doing here is, so if you think about it like this, we are just summing periodic functions. It's kind of continuous sums of periodic functions. Or you can be formal and then change x to x plus gamma, and using periodicity of g, you notice that this is periodic. So let me just write it, g periodic implies that LFG is gamma periodic too. That's pretty elementary. So it's really a function that is an operator that takes us from here to there. Now the question is this an integral operator? Because the way that it's written here, it's not clear that this is an integral operator, because this function f is completely a random function, except that it has some decay at infinity, right? Otherwise, there's no periodic behavior, so I cannot say f is an element of, or f of x minus y as a function here, right? And this integration is over Rn, is not over Rn over gamma. So our first task to do is to make sure we understand that this function is actually is an integral operator. Claim is that LF is an integral operator. With kernel k of x and y equal to sum f of x minus y plus gamma, gamma belonging to gamma. Okay, first of all, this infinite sum is convergent because if you take, it's rapidly convergent. If you take x and y, you're summing over gamma, so you're going to infinity, and this is rapid decay. So again, this is convergent. So there's no problem with this sum. Now, the next thing is that this function k is actually doubly periodic in each variable, right? So in fact, this has the property that k of x plus gamma and y is equal to k of x, y plus gamma is equal to k of x and y for all gamma in the lattice. I mean, this is quite clear because we just averaged over gamma. So when you shift, you can shift the summation here, but this is a lattice, so you're summing over the lattice again in a different order, so this is a second. So that's quite clear that this function is periodic in each variable, so we can think of k then as a result, as a function on L2 of torus cross torus. So k belongs to L2 of Rn mod gamma cross Rn mod gamma. So it's a kernel. Now, the only thing that's left is to show that this integral f x minus y g of y dy over Rn is equal to the integral k of x and y g of y dy over Rn mod gamma. So this is what we have to show now, because we have a proposal for the kernel, which is in the right place, but we have still to show this. So this is for any g belonging to L2 of x mod, sorry, Rn mod gamma. Now, obviously, what you can do, you can use periodicity of G, and you can write integration over Rn as sum of integrals over blocks or cells of the. So let me write it. Pick a fundamental domain. D for D for gamma. So basically what we're saying is that this is a fundamental domain D, and you can pave Rn using translates of this fundamental domain, right? So so this is a fundamental domain you chose, and then you can translate at all points with respect to this gamma lattice, and then you pave Rn. So you can just write integration over Rn as sums of integrals over translates of D. Okay, so then write integral f of x minus y g of y dy over Rn as sum integration over D plus gamma, gamma in gamma. Yes, f of x minus y g of y dy. So of course you can write it as sum gamma in gamma integral D plus gamma. I mean, just switch the variable, just write it f of y as we had before, g of x minus y. Y. Okay, so, but okay, so this, yes, so this you can write it as sum over gamma, integral D plus gamma, f of y plus gamma, g of x minus y minus gamma, so changing variable, gamma dy, The trick is that you should get just x, and they cancel, so you just get, if you sum these two values, you get x. That's your check, and that's okay. But the function g is periodic, so this term drops. So this is equal to sum over gamma, integral t plus gamma, f of y plus gamma. Okay, I'm going to switch the order because already shift is done. So let me just write it here. So this is, yeah. So this means just let me write the last step, which is, so there's integral over d, the sum over gamma, sorry, f of y plus gamma g of x minus y dy. And that's the sum that defined this function. So let's call this function, say, f of y, which is this function, sum of these things. So it's a gamma periodic function. And this is exactly the kernel function that, if you write it in terms of x minus y, is this kernel function k that we have over there, right? So, yes, right, okay, yeah, okay. So that's it. That's the end of the proof of the fact that this function is the kernel of integral kernel of that operator, and we just showed that this operator that I wrote as convolution is indeed an integral operator. So basically we showed that convolution. So let's remember this in one sentence: convolution operator. Maybe our convolution operator is an integral operator. Okay, so then we can, and in fact, if you know you work with continuous functions and rapid decay, and this sort of basic analytic things are in order, then we can use the trace formula. So can apply the trace formula. I mean, the original trace formula, and then you get the following statement, that this geometric trace of xx dx over Rn mod gamma is equal to sum lambda I. So what is this? Now, because this operator was of the form capital F of x minus y, so as you just, you see, so what is k of x and y? Remember, was sum f of x minus y plus gamma in gamma, right? This was our kernel. We just verified over that this is our kernel, right? Okay, now if you put x equal to y, you're on the diagonal, in other words, then these terms cancel, so this is equal to sum f of gamma in gamma, so it's a constant. So the function, in this case, the kernel on the diagonal becomes a constant function. So if you are integrating over Rn mod gamma, this is just, you're integrating over one period or one fundamental domain, and that's exactly volume of gamma. Okay, so that's, so left-hand side of trace formula is equal to volume of gamma times sum f of gamma in gamma. So far we were able to at least produce part of the Poisson summation formula, I mean, half of it. So it just says that this geometric side is really summing F over lattice elements. There is this factor of volume of gamma, but that's fine. But now the question is, what are the eigenvalues of this operator AK, right? That's what are the eigenvalues. And in fact, what are the eigenfunctions? So we want to know what are the eigenvalues and what are the eigenfunctions of this, and then hopefully we can reproduce Poisson summation by this argument. Now, here is, again, everything we are doing here is very, very general. If you remember and work out through these steps, you notice that the arguments are kind of has a universal character. It can be applied in many, many situations. Now, the next step is also like that. So what I'm going to argue is that actually the eigenfunctions of this operator AK are in fact characters of this abelian group Rn mod gamma. So let me just, because I need this concept later on anyhow, so let me introduce the idea of character of a group. So this is the, I mean, the right concept is abelian character. I mean, abelian character of a locally compact group. I'm not assuming the group is abelian itself. It's just a function chi from G to U1, which is the set of all complex numbers such that absolute value of Z is equal to continuous. And of course, chi of G1, G2 is equal to chi G1, chi G2. Of course, chi of 1.
Did his laptop run out of battery or something?
That has happened before. Probably is what happened.
It's just getting to the exciting part.
Maybe someone should email him. I mean,
Oh, that's true. He might just keep
I
going.
will call him. I will call him.
I mean, this does not happen in live lectures.
I can imagine him saying like, "Does anyone have any questions? You're all not asking any questions. You should ask questions. Very important."
Yeah, sorry about that. I forgot to connect my computer, so I went out of battery. So just okay. It looks like yeah, it's looked like we are recording. That's good. So let me just Okay, so now we're good. Okay, so I don't know how much of the last episode you saw. Did you get these characters? No. Okay, so you saw up to here, right? Okay, so
Yeah.
what's that?
I said yes.
Okay, good. So up to here is okay. Then I introduced the idea of abelian character of a locally compact group, which are just one-dimensional representations of the group, if you want. And these are, if the group is abelian, these are all the irreducible representations, but anyhow, we can independently talk about them. So they have this property. So this map has to be continuous, of course. Okay, so yeah. Okay, so now the thing is, the general idea is that so characters are eigenfunctions of convolution operators. So because we want to produce the right-hand side in a kind of good way, right? So we better know what are the eigenvalues and eigenfunctions of this. So first of all, let G in this case be equal to, I mean, this group, which is Rn mod gamma. This is the torus. So it's a compact abelian group. Then for every k belonging to gamma star, this function chi k of x equal to e to the 2 pi I x dot e to 2 pi I x dot k. This is a character. I mean, you can check that it has these properties. Is a character of G. And in fact, it's not difficult to show using a little bit of basic analysis that these are all the characters. These are all the characters of G. Okay, so the characters of this group, this torus, which is obtained by Rn mod gamma, is kind of labeled or indexed by the dual group, which is gamma star, the reciprocal or dual lattice. We call it dual group also because it's a group in the dual space as well. And these are the ones. Now, the claim is that these guys are actually eigenfunctions of this convolution operator with eigenvalues that we know what they are. So let me just write it as a lemma, and you'll see that with this lemma in place, everything is known. So lemma is that a k of, now this is unfortunate because a k, oh sorry, chi, okay, chi k. Now these two k's are different. So let me call it chi, yeah, chi k, yeah, is equal to f hat of k chi k for any character k of Rn mod gamma, i.e. Characters are eigenfunctions of convolution operators with eigenvalues F hat okay. So proof. So we have to prove this lemma. It is a simple lemma. So what we have to show? We have to show that if you apply this operator with that, you get that. So what is that operator now? So of course, I mean this operator is just okay. So we have got AK. I mean this. Okay, so maybe I just say LF. Yeah, that's much better. LF of chi k equal to F hat. Okay, so what is LF? LF of chi k, it was F convolution with chi k. So this LF of chi k of x is integral f of integral over Rn of x minus y. So I would say f of y chi k of y minus x, right? And then this was dy. So this is our very original definition of this operator, right? This was our original definition. Okay, so now let's just compute the integral. That's not difficult. So the integral now is equal to. Okay, so this is equal. We just have to replace chi k by its value. So this is integral over Rn f of y e to the 2 pi I e to the 2 pi I. Okay, so what was y minus x k dot y minus x dy. No, x minus y, sorry. Yes, it has to be that. So that's equal, but using the property of explanation, you can write it as Rn f of y e to the 2 pi I minus 2 pi I ky dy. But then this factor e to the 2 pi I k dot x, there's no y dependence here, so this comes out, right? Okay, that's it. So this, I mean, this quantity, we know what it is. This is f hat at k, right? So e to the, but this is chi k. So the characters are eigenfunctions, and the corresponding eigenvalues is the Fourier transform of f on the label of the character, which is, in this case, we know that's a dot x. Okay, so now the question is, are there any other eigenvalues or eigenfunctions? How do we know that we have found them all? Because in the state, in this trace formula that Litsky's theorem that I wrote, the right-hand side was summing over all eigenvalues. We cannot miss any eigenvalues. And this is, in fact, the case because these functions, Fourier basis, form a complete orthogonal basis for L2 of okay, so since, so let me write it like that, since the set of all e to the 2 pi I k dot x k belonging to gamma star, with the 2 pi I k dot x k belonging to gamma star, is an orthonormal or orthogonal basis, I would say. There is a question of normalization, but it doesn't matter here. An orthogonal basis for the 2 of Rn mod gamma, we are done. There is no other, in other words, I'm saying there is no other eigenfunction or eigenvalues. Okay, so then the original trace formula tells us that so we just showed that volume of gamma sum f of gamma in gamma is equal to sum f hat of gamma, of k gamma star. And of course, if you divide, you get the original Poisson summation formula. So this is, yes, sir. So TSF, in fact, if you think about it like this, again, yeah, indeed, is an example of a trace formula. So that really explains why Poisson summation formula is called a trace formula, because indeed it involves computing trace of an operator in 2 different ways. But now, my original proof that I gave on Monday, this idea was not clear. I mean, indeed, there are always these 2 proofs. The first proof is quick, but you don't see much. The second proof is a bit more involved, because it involves some very, very universal general ideas. But the value of the second proof, this proof, is that it can be repeated in many, many contexts, and it will produce many, many different trace formulas. That's the message of this 1 hour we spent, was just to remember this fact that, yeah, the PSF is just an instance of a very general trace formula. Now, so the next, so recall what we did after this. That was also very important. Then we took a very, very special cherished function. So we took this function Gaussian, right? I mean, it's a very, it's a unique function. I mean, you can't just compete with Gaussian. So this was a norm of x squared, right? For any n. So the Gaussian, we picked Gaussian, and I said that.
Question?
Yes.
So I'm a bit confused. In this Poisson summation formula on the right-hand side, clearly we have the sum of all eigenvalues of this convolution operator.
Yes.
But on the left-hand side, we don't really have the integral on the diagonal, but only over the special values, right? Over the lattice.
No, but remember, we do have integral over the diagonal. You see, the way this, there was a simplification. You see, what we did integral k of xx, right? Dx over this fundamental domain D, right? But then k of xx is equal to, well, what was k of x and y? It just turns out to be sum. I mean, I proved that this is sum of x minus y plus gamma. So if x is equal to y, then this cancels, so this becomes integration of a constant, right? So the constant is just f of gamma belonging to gamma, dx. And this drops out, so this is sum f of gamma is a constant. But then, of course, the volume of the space has to be there. So this is volume of, so integration is over d, volume of d. and which is volume of gamma. Yeah?
Thank you.
You see the point, right? Yeah, so you should not think that we are integrating over these lattice points. No, we are not summing, well, we are summing over lattice point, but it's a sum came as a result of integration, but this was a lucky situation, and it always is like this, at least in the case of abelian groups, that we have this situation, and then get this. Okay, so then we took this, as I said, very cherished function Gaussian, f hat of C. I said that it's a fact, very well known, of course, is equal to that, right? And okay, then Poisson summation formula gave us so applied to lattice. Family of lattices, right? To lattices root T gamma. So if you take any lattice, then you apply the family of lattices, and then we got the sum, that sum exponential of minus pi norm of gamma squared T. Well, gamma belonging to gamma turns out to be equal to T to the power minus n over 2. Was it, yes, over volume of gamma times then the sum exponential of minus pi norm of k squared. Okay, no, it was a pi. So where was the pi? Pi, I mean, the t is down. Yeah, pi is up. Yes, pi is up. T is down, and this is now k belongs to gamma star. So this is the formula that we derived. You see, we could not finish the proof of this Milnor counterexample or other application just by using this formula, right? This is kind of just the general trace formula. The Poisson summation formula by itself does not prove anything, well, except a general fact. But the question is, what kind of lattices you choose and what kind of functions you have. You have two choices to play with. Choose your lattice, choose your function, then you're proving some very interesting things. In this case, we derived this formula, and I said that if gamma is equal to, so for unimodular lattice, for self-dual lattices, for example, then we got this formula, the amazing formula that, yeah, so this Z gamma of T, okay, so now I don't know what was my notation for this partition function. Did I use 4 pi t or pi t? I'm not sure. Did I use 4 pi t? Or... So this is the sum on the left hand side is equal to and volume of gamma. In particular, then we got, of course, this is equal to t to the power minus n over 2 z gamma of 1 over t. Yes. We derived, I mean, it's exactly the same formula, just introduce this notation. Now, if you think about it, I mean, so what does it say? It just, so you see, these gammas is, this is the kind of geodesic spectrum. It's called the length spectrum. spectrum of gamma. So these are lengths of kind of primitive geodesics. They're just, I mean, lengths of all geodesics. Sorry, not primitive. All geodesics, as I
Oh.
mentioned last time. And
But isn't it closed?
sorry.
Closed.
Yes, absolutely. Closed geodesics. Yeah, I mean, I argued that if you have a geodesic on the torus, lift it upstairs. If it is closed, then it's going to connect one lattice point to another lattice point. I mean, the difference is going to be like that. Okay, and then for the right-hand side, this K, of course, this is the Laplace spectrum. So basically, this result shows that they determine each other. The Laplace spectrum determines the length spectrum and vice versa because of this relation. So Laplace spectrum is something quantum mechanical, and this length spectrum is classical. It's just the periodic orbits, closed orbits of a particle that's moving on the torus without any interaction force, without any external force, just moving along geodesics as a result of that. So, and this, the fact that there is a correspondence between these two things is that's what actually we used in the proof. And this is a very, very deep fact, and we want to see some of the consequences of this soon. So, okay, so of course, n is the dimension of this torus gamma, and so I think maybe you have questions, and then I'll stop, and then we will come back in 5 minutes. Yeah, you have any question? Any comments or questions?
I have a question. So you said that so given a choice of lattice and given a choice of function, you get one of those trace formulas. You can use the trace formula to derive an equation. But in order for this equation to be a functional equation relating a function to itself, you will want the function to be the Fourier transform of itself, and you would also want the lattice to be self-dual, right?
Yes, that's true.
Yeah. So in that case, it seems that that there isn't much choice if you want to get a functional equation.
Yes, indeed. Yeah, indeed. There isn't much choice involved, and so part of the deal is to choose your function in the right way. Now, for abelian groups, it's exponential, Gaussian. I mean, for non-abelian groups that define, we'll see it soon actually, that will define these hyperbolic surfaces. That function is a very non-trivial function. So that function was chosen by, was discovered by Selberg in 1950. So that's in his Selberg trace form. So we'll talk about that, but gradually, I mean, we have to build some understanding from basic things now, and then we move to that, towards that. So yeah, exactly. That's a very good point. The art is to know what functions to choose, what lattices to choose. Yeah, exactly. Now, one more thing is that, okay, so I said this for torus, but then when we come back, I will immediately indicate that this result actually holds for all locally compact abelian groups. So this is a very general idea of trace formulas for locally compact abelian groups. So I mean, in other words, Poisson summation formula works for all locally compact abelian groups. So I will write down the statement, and then we will look at some examples of that, and then we go to this hyperbolic geometry. So this is where. Okay, guys. So sorry, I went over time for our break. 5 minutes break is okay, right? Yeah. Okay. So then we can stop actually here. So okay, pause. Okay, so here is a nice exercise. So yeah, I want you to show that two lattices are two that are isospectral are isometric. So we cannot construct these lattices in R2, at least. Okay, so, well, I mean, this is something very well known and kind of elementary, but it's good to do. So now let me just write down this Poisson summation formula. And so let me write it like this: is an abelian trace formula. In general, so the general statement is this: for any locally compact abelian group G and a discrete, actually you don't even have to assume discrete, but that's okay, and a discrete co-compact subgroup H inside G, and for any suitable function, suitable means it has decay at infinity, f from G to C, we have integral, so let me write it as sum of f of h belonging to h, is equal to integral over okay, so we just write it like this. This is going to be equal to right. So let me put it like this. 1 over volume of G mod gamma sum f hat of k belonging to G mod gamma hat. So what is this f hat? Is the Fourier transform of f. So it's a function f hat, the function from the dual group of G to C, which is defined like this: f hat of k is equal to integral f of G. Okay, so this is so on a character chi. So this is chi of G bar dg over G. Now, what is G hat? is the dual group. Which is the set of all characters of G on C. I mean, it goes to U1 really, but that's okay. So it's a group. It's again a locally compact abelian group. It has a natural topology, which is compact open topology. It doesn't matter right for us right now, but there is, and there is such a statement. So this G mod gamma is compact. By assumption is a compact group. So this set then is, so this implies that G mod gamma hat is a discrete set. The duals of compact groups are just discrete sets. So that's what we have. And so this statement is the general form of this Poisson summation formula for locally compact abelian groups. It can be done even more general than that because, I mean, you don't have to deal with summation. You can just have a closed subgroup which need not be discrete and replace sum by integration here, and then on the right hand side you have this sum. So if you use hard measure, and then you can prove it. What I want you to do is a nice exercise here is this case. So let me just give you a nice exercise. I want you to prove it for finite abelian group. So exercise is this. Prove this for finite abelian groups. So you have this, you know, finite abelian group subgroup, and the claim is that yes, sum for any f. There's no growth condition, no continuity, nothing. Just everything is simple. This is just says that prove that sum f of h belonging to h, and then there is a normalization here. Oh, this is h. Sorry. This is h also. But I could have chosen gamma because, yeah, this is h. Sorry, just, yeah. So this is equal to sum f hat k belonging to G mod h hat. So there is a factor here. I believe volume of h should be here. Yeah, and then volume of G comes here. Well, I mean, volume is nothing but the order of G, right? Under the Haar measure in this case. Yes, it's very simple. So I highly recommend you to do this. This is a nice exercise. The only thing you have to know is that the characters of these abelian groups, well, we know what they are. They are like exponential of 2 pi I. So just start with cyclic groups. And so, for example, take a cyclic group and take a subgroup of that and try to prove this. And then you can just decompose any group to any finite abelian group as products of cyclic groups, and then you can prove the result. Or you can just use this integral operator formulation I gave and follow that. That would also give you the same. The argument that we gave for the torus works exactly in this case as well. Okay, so this is now a general abelian trace formula, obviously because we are applying to, we can just say this for abelian groups and subgroups and these things. But now the question is there any non-abelian version of this, right? And in fact, there is, but that becomes much harder because analyzing these things as we really use change of variables and move the, you know, these integrations across different signs. So that's not going to be easily done like that. So we have to be much more careful, and then you get a more involved expression. But essentially, something like this again is true. So you just write that this geometric sum is equal to some spectral sum. But in that case, you have to bring in representation theory of the group into the picture, and you have to use higher dimensional representations of the group. So just one-dimensional representations are not enough. So that's much more involved, and we'll look at some cases of that for sure. I think right now, so this is what I wanted to say about the general philosophy of this trace formula. So now you can see that these trace formulas are something quite general and universal. I mean, but then they come from something very, very basic, which is, that's what we started with, you know, some AII equal to some lambda I. That's the essence of things. Everything after that, we have to take good functions at the end, and then good lattices, and da da da. So, yeah. Okay. Any questions? Or?
I have a question.
Yes.
So, why do we care about like a trace formulas on non-abelian groups? Where do they arise?
Oh yes, exactly. I mean, so what happens? That's my next topic actually, because we are going to go now to non-abelian groups. But yeah, that's exactly kind of prompts me to what I wanted to discuss. So that's the spectral theory or spectral geometry of hyperbolic Riemann surfaces. So let's look at so this H. Imagine part of Z is positive, right? So this space is called hyperbolic plane. It's also called Poincare upper half plane, as we discussed, right? So there is a metric here that was in one of your exercises. So the metric was this: ds squared equal to dx squared plus dy squared over y squared. This is called Poincare metric. So then I think there was another exercise to show that actually curvature of this metric is -1. Constant. And if it's constant is equal to -1. So this is a Riemannian manifold. It's not compact, it's non-compact. But it's complete, connected, constant curvature -1 Riemannian manifold of dimension 2, and is simply connected. And as such, it's the unique such object. So there exists only one simply connected complete Riemannian manifold of dimension equal to 2 with constant curvature equal to -1. And this is this point. So it's a universal object. So basically we have these three objects, right? We have this plane R2, its curvature is equal to 0, sphere S2, curvature is equal to 1, and H, curvature is equal to -1. So up to scaling the curvature or metric, there are these three classes of simply connected, complete Riemannian manifolds of constant curvature. Either constant curvature 0, which is R2, or 1, which is S2 then, or -1, which is this one. So that's one kind of thing you have to bear in mind. These are called symmetric spaces of dimension 2, so we have to bear in mind that these objects are very, very universal. So we are here now, for some reason we are looking at. And then there is a group, now answering your question, there is a group that's acting on this space. That's the group SL2R, right? So how does it act? It acts like this. If you have a matrix G and a point here, sends it to something which is called GZ, which is nothing but AZ plus B over CZ plus D. But G, of course, is just a matrix ABCD, right? Now, it's very easy to check that the imaginary part of GZ is equal to imaginary part of Z over absolute value of CZ plus D squared. You can just check this. And as a result, I mean, of course, AD minus BC is equal to 1, right? As a result, okay, you can check two things. First of all, this is an action. This star is an action. I mean, G1, G2 of Z is equal to G1 times G2 of Z. I mean, this is not totally obvious, right? It's a very strange kind of thing that these two things actually match, because one of them we are using matrix multiplication. In the other one, we are using compositions of Mobius transformations. So the fact that they match is kind of something is there. So it's kind of interesting. And also sends, and this relation shows that it sends upper half plane H bijectively to H. Now, you can check that actually this is this action is isometric. This you can check without much effort. That's so, you know, I mean, yeah, if you pull back isometric, of course, I mean, I'm talking about Poincare metric, right? With respect to Poincare. Now, what is true is that actually the group of isometries of this space, is in fact SL2R up to this center business and up to orientation. So let me write this statement, which we need anyhow. So I will finish in a second now, actually, because it's going over time is not nice. Yeah. So fact is that isometry class of H is equal to PSL2R, which is SL2R divided by plus minus 1. You see, this is the center, right? Of SL2R. And of course, I mean, this action AZ plus B over CZ plus D, if you multiply everything by minus 1, you're going to get the same action. So that doesn't change anything. So you have to divide by the center. So you go into this. But okay, so this exercise you do here, this check, only proves one direction, but you have to show that there are no other orientation preserving isometries. That takes a little bit of work, but it's not terribly difficult. But that's okay. So we have that. Okay, so then the idea is this: if imagine you have some discrete subgroup of this, okay, subset of PSL2R. I mean, let's take subset of this, doesn't matter. A discrete subgroup. So, discrete subgroup such that, okay, if you divide H by this discrete subgroup, then you're going to get, again, a surface. So, acting freely, and so there is a term for that. It's called properly discontinuously. So, I mean, the modern terminology is properly, but properly discontinuously is also used. But this is older terminology. But what really it means is that if you take H and divide it by this gamma, this is a again is a Riemannian matrix, the Riemannian surface. So we have got now from H. So in other words, this is a covering map. So this induces a metric of constant curvature minus 1 on H over gamma. Okay, well, this we saw. I mean, this is a very simple thing. So because here there is a Riemannian metric, you induce a Riemannian metric on this quotient space because this is you declare this covering map to be an isometry, to be a local isometry. Then the curvature is preserved, and you get that. So now the amazing fact is that actually for example, all compact Riemann surfaces can be obtained by this method. So, so this is uniformization theorem. I have to finish, sorry. All hyperbolic, I mean all genus bigger than or equal to 2 Riemann surfaces. Okay. So in other words, study of Riemann surfaces is nothing but the study of such quotients. Now, this quotient you can understand in terms of quotient of, but let's see what is H. H is equal to itself is equal to SL2R by some stabilizer. Because as we will see soon, in fact, this action here is transitive, so you can write this by some stabilizer. So you have a double quotient there. So what happens is that this manifold M is equal to SL to R divided by some isometry group, which is K, and by some discrete subgroup, which is gamma. So it's a double quotient space. And that's what we care about. If you understand kind of spectral theory and geometry of these double quotient spaces, then you understand the things for Riemann surfaces. So that's why we care about these trace formulas. That's one reason one answer to your question. But of course, I mean, I went a bit too fast at the end. I have to recall some of these formulas after this one. Sorry, I went over time. I'm terribly sorry. Any questions, or I guess we can just I can just stop the video then. Yeah. Okay, so stop recording. Yes.